The apparatus that we have set up here is used to pass a direct current through a wire. Magnets on the iron yoke produce a magnetic field which is perpendicular to the wire. When we turn on the current, we can see that the balance reading increases. This is due to the fact that the magnets are exerting a force on the wire which is upwards, whilst the wire then exerts a force on the magnets which is downwards in accordance with Newton's third law of motion. The iron yoke is therefore pressed downwards onto the balance and the balance reading has increased. We can see that increasing the size of the current increases the force, and in fact if we double the current we should produce double the force. Reversing the direction of the current will reverse the direction of the forces, so the balance reading now changes to a negative value, as we can see. Reducing the current again produces less force. Increasing the current again produces more force. The circle with a cross in indicates a wire carrying a current into the screen. We can represent the magnetic field around this wire with a series of concentric circles. The circles must become more widely spaced, indicating that the field gets weaker as we move further away from the wire. We can work out the direction of the field using the right hand grip rule. If you take your right hand and you coil up your fingers, point your thumb along the direction of the current, which in this case will be into the screen, and then as you take a right hand grip, your fingers will point along the direction of the field lines. So you can see here for a wire carrying a current into the screen, the field lines will be clockwise. If the wire was carrying a field out of the screen, point the thumb back towards you, and this time as you take your right hand grip, you should see that your fingers are pointing around anti-clockwise. So there we go, we can predict the direction of the field lines around a current carrying conductor. The magnetic field between the magnets that we had on our iron yoke is uniform, and we can represent that with a series of straight, equally spaced field lines. When we place the wire inside the iron yoke, the two magnetic fields will interact. In the example shown, the strength of the field to the right of the wire is reinforced, as the magnetic fields of both the magnets and the current carrying conductor are in the same direction. The strength of the field here is illustrated by very close magnetic flux lines. To the left of the wire, the interacting magnetic fields are in opposite directions, and we actually produce what is called a neutral point, where the magnetic fields will cancel each other out at one particular point. We can imagine these magnetic flux lines are pieces of elastic which have been stretched and they're trying to snap back into position. They therefore act like a catapult and will exert a force on the wire as they try to fire it out to the left. We have seen already that doubling the current in a conductor will produce double the magnetic force on the conductor. And in fact, the magnetic force depends similarly on the magnetic flux density, and that's the strength of the magnetic field, and also the length of the conductor in that magnetic field. We have F equals BIL, where F is the force on the current carrying conductor, B is the magnetic flux density, I is the current in the conductor, and L is the length of the conductor in the magnetic field. One important point to make here, however, is that in order to get that full F equals BIL force, the magnetic flux density and the current must be at right angles to one another. If they're not, what we will have to do is to work out the component of the magnetic flux density that is acting at right angles to the current in the conductor. Magnetic flux density is measured in Tesla, and the Tesla is actually defined through this formula. So a magnetic flux density of 1 Tesla exists if a current carrying conductor carrying a current of 1 amp perpendicular to the magnetic field experiences a force of 1 Newton per meter of its length. So 1 Tesla is 1 Newton per amp per meter. Now, we can predict the direction of the magnetic force using Fleming's left-hand rule. So if we arrange our thumb, first finger and second finger of our left hand at right angles to one another, then the thumb will be the direction of the force. Thrust, you think thrust is another way of saying force. First finger, F for first finger, stands for the field direction. And second finger, if we put the accent on the C of second, second finger is the direction of the current. So put a first finger along the field direction, second finger along the direction of the current. Our thumb will be pointing along the direction of the magnetic force. What we've got here is some apparatus again for demonstrating the F equals BIL force. So what we've got here is two straight wires with a rider, a third copper wire riding on the top of them. And basically we've got this arranged here so that the wire at the back there is at the positive terminal and the wire closer to the front is on the negative terminal. And so we're going to have a conventional current which is going to flow through the riding wire out towards us. Now what I'm going to do here is bring up a pair of magnets so that the magnetic field will be acting downwards. Now we can use the left-hand rule to predict the direction of the force that will act on our riding wire. So if we point our first finger downwards and our second finger, the direction of the current in that riding wire is going to be out towards us, you should find that your thumb will be pointing to the right. We bring the magnet in and you can see that the wire moves to the right. Now if we reverse the direction of the magnets, turn them around, we'll see now that the force on the wire will be to the left, because in this case the first finger, the field is pointing upwards. Second finger again, the current is still coming out of that wire towards us, from the back wire to the front one. So the thumb now is pointing to the left. We're going to have a force that will act to the left. And there we go, you can see the riding wire is moving to the left across there. Turn it around again. That will reverse the direction of the force. You can clearly see it coming back to the right. We can do that as many times as we like. Here we have two questions where we're going to use the formula F equals BIL along with Fleming's left-hand rule to come to the solution. So the question is, find the size and direction of the magnetic force on the conductor acting per meter of that conductor in each of these situations. So here on the left, part A, we've got a current carrying conductor carrying a current to the right, and we've got a magnetic field. Well, the crosses here indicate the magnetic field is acting actually into the board, into the screen. I always think, imagine a dart. If it's you're seeing a cross, you're seeing like the cross of the dart at the back. It's moving away from you. And so it's going into the screen, into the page if it was a worksheet. So magnetic field into the screen, current acting to the right. They're at right angles to each other. We can use the formula F equals BIL, provided they're at right angles, which they are. So we have 40 millitesla. Don't forget, prefix milli means times 10 to the minus 3. Tesla, capital T, is the unit of magnetic flux density. That's the strength of the magnetic field. We have our current, 250 milliamps. That's 250 times 10 to the minus 3 of an amp. And we're asked to work out the force on the conductor per meter of its length. So we're going to use a length of 1 meter. I'm working out the force acting on each meter length of this conductor. And there we are. All we have to do then is put those numbers into our calculator and work out the answer. And there we have it, 0.010 newtons or 10 millinewtons. What about this second example? Well, once again, we're working out the force on a conductor in a magnetic field. So the formula we want is F equals BIL. But don't forget, the current and the magnetic field must be at right angles to one another when we're working out this force F. Here clearly they're not at right angles. The arrows representing the magnetic field strength and the current are both acting in the plane of the screen here, but they're not at right angles. The angle between them is 30 degrees. So what we are going to have to do really is split this magnetic field here, in this magnetic field vector, into two components, one acting perpendicular to the field and one acting at right angles. So we're going to take this arrow here, we're going to split it into two that act at right angles, and it's this component here, the vertical component, that we are actually interested in. So if we know that this is 40 millitesla here, this angle here has got to be 60 degrees. Now that's 40 millitesla on that side. And we want here the side adjacent to the angle. So if we think about it, we know that cos is adjacent over hypotenuse, remember SOHCAHTOA. So cosine 60 degrees has got to equal this adjacent side, the vertical component is the side adjacent to the angle, it's the one we want, over the hypotenuse, which we know is 40 millitesla. So our magnetic flux density that we're going to put in this case is not 40 millitesla. When we rearrange this, it's 40 millitesla at cos 60. So the force on this conductor, 40 times 10 to the minus 3 cosine 60 multiplied by the current, which is 250 times 10 to the minus 3 amps, 0.25 amps of current here, and multiply that then by the length. Well, we want the force per meter, so we're just going to put the length in as 1 meter, and once again we can work out the force. And there we go, the force acting on this occasion is 5 times 10 to the minus 3 newtons. Well, of course, the other thing we were asked for these two problems was the direction of the force as well as its size. So let's see if we can work that out using the left-hand rule. So on this case here, in part A, if we think about it, second finger, direction of the current here, use your left-hand rule, second finger, make sure that's pointing left to right. Holding your thumb, first finger and second finger all at right angles. If the second finger is to the right, the first finger wants to be going into the screen. And that means here that we've got our thumb indicating the force direction pointing upwards. So here it's 10 millinewtons acting upwards. What about on this occasion here, this one? Well, we know we've got, again, our second finger going left to right. This time the field direction, or the component of the field that we used, was acting straight down. And that means if we turn our hand round, holding the thumb, first finger and second finger at right angles to each other, we've got our first finger pointing downwards, our second finger pointing to the right, and our thumb then is going into the screen. So here that would be into the screen or into the page if you're looking at this on an exam paper or on a worksheet. And there we go, that's using force on a conductor in a magnetic field, Fleming's left-hand rule, answering some typical questions. So again, two more problems to finish off. Again, find the size and direction of the magnetic force on the conductor acting per meter of its length. This time in part A, again we've got a current of 300 milliamps and a magnetic field of flux density 80 millitesla. But this time, if you notice, the current and the magnetic field are both in the same direction. Now remember, if we're using F equals BIL to calculate the size of the magnetic force, the magnetic flux density is the magnetic flux density that's acting perpendicular to the current. Well, because they're acting here along the same line, the component of the magnetic flux density perpendicular to the direction of the current is actually 0. Here, if we were going to try and work out the component acting perpendicular, it would be 80 millitesla cos 90. Cos 90 is 0. So there is no magnetic field acting perpendicular to this wire at all. So 0 times 300 milliamps is 0. So the force here is 0. We've got 0 force acting. 0 newtons. There's no force, there's no magnetic force here acting at all on this conductor, because the magnetic field is in the same direction as the current. There is no component of the field acting perpendicular to the current. What about part B? Well, this time here the blue dot indicates a current coming out of the screen. So usually the convention is if we've got a cross, that indicates a current going into the screen. The dot indicates it coming out of the screen. The cross is like looking at the back of a dart going away from you, and the dot is like looking at the point of the dart coming towards you. So the current is towards us, and the magnetic field is acting to the right. So they are acting at a 90-degree angle. So we can use F equals BIL. We've got 80 millitesla magnetic flux density, 300 milliamps, so 300 times 10 to the minus 3 amps current. And we're wanting the force acting on a meter length of the wire. So L is 1 meter. We can work out then the size of the force. And we reach an answer of 0.024 newtons, or if you like, 24 millinewtons. Now what about the direction? Well, again, we have to use the Fleming left-hand rule. Thumb, first finger and second finger at right angles. Second finger needs to point out of the screen because it's coming out towards us. First finger field should be going to the right, left to right, and that means our thumb is pointing upwards. So here the force is upwards.